Okay. Any questions? So we saw yesterday that by demand engage invariance gets you to cross-engage invariance. This theory does the following. There is a W boson and it couples like this. Every up component couples to the down component here. G prime. This is the culprit. This is the messenger of the original weak interaction of beta decay. We don't know its mass. The theory cannot per se tell you the mass. Actually, if the symmetry is there, it would be even massless. We also said, moreover, so this is one thing, if there is a photon A mu so that it couples to the well-known electromagnetic current that I can write at F bar gamma mu QF, then it follows that there is a Z boson so that it couples in a well-defined universal manner also cosine theta W, Z mu, F bar, gamma mu, T3 minus Q, sine squared theta W, F. Notice what we found. This was very important. We found out that the photon cannot be just in SU2 or U1. It has a well-defined form, sine theta W, A mu 3, plus cosine theta W, B mu. B mu is the gauge boson associated with U1. These are the TA, sorry, why am I saying TA? I'm talking about gauge bosons. A mu A. A's 1, 2, 3. This is very important. This is why we call the Electroweak theory. And sometimes we say that there is electroweak unification. In spite of the fact that we have to sort of provide this parameter, theta W. After all, let's write it here, tangent theta W. Something that has to be measured. You and I cannot predict it. It comes from two different groups. If I were to predict it, I would have to start with one group. And at the end of the course, we'll talk about that. And of course, Z mu must be orthogonal to A mu. I won't even write it. I wrote it before. You can immediately figure it out. Since MA is 0, when I say photon, of course, or almost 0, if the symmetry was there because they live in the same multiplet, then W and Z would have the same mass. So by the fact that MA, MW and MZ are different from zero, and we know they have to be different zero, you know it immediately because otherwise one would have seen them directly. They also mediated very weak interaction, therefore they had to be massive, not just non-zero, but actually rather massive. You knew immediately that MW, MZ would be of the order of 100 GeV, or not less than that. Let me write maybe more. MW and MZ, when I say around 100, I mean the order of magnitude, in order to explain why weak interactions are weak at low energies. We talked about it yesterday. This, of course, implies that the symmetry is broken. Well, that's not surprising, because I told you that neutrino and electron live in the same multiplet, and m nu is basically zero. It's so tiny. I'll come back to neutrino mass. Well, someone wants to tell me how light is neutrino? Someone knows? Roughly? Anybody?
Around 1 eV.
Right. Neutrino mass is less than 1 eV. So this also tells you that SU2 must be broken. If you have a good symmetry, the particles will have the same mass. It's interesting in the up and down quark. You know up and down quark? A comment en passant now, to come back. It's hard to even think what I mean by masses. You know, quarks are confined. Nobody ever saw a quark. What is a quark? Quark is something that makes a proton or a neutron. There is this interesting thing that the mass of the proton is equal to mass of the neutron. It's almost the same. Very interesting thing that made Heisenberg and Majorana suggest that there is what we call an isospin symmetry of strong interactions, in which proton and neutron would form a doublet. But it also tells you that m up is roughly equal to m down. Here roughly, okay, here actually even I could put a quick question mark, because when we talk about proton mass towards the end, we'll have to learn something interesting, that the mass does not come only from the quarks inside. Actually, we will learn, and maybe you know, that the mass of the proton and neutron comes by and large from the kinetic energy. This guy proton, you know, UUD, actually it's full of stuff which is called glue. The gauge bosons of SU3, there is a great dynamics here. There is sort of a crazy motion, okay? It's a very dynamical system. Imagine running with your shopping bag tightly closed. As you're running, the things may go crazy inside the shopping bags, but they don't go out because you're making sure that it's tight enough, okay? This is just en passant. We'll come back to that. So I don't really know what M up and N M down are, but we know today that M up, whatever I mean by that, there is a way of knowing that we'll talk about. Again, we know that SU2 is broke. So please keep in mind, we have to have a way of breaking the symmetry. We understood that. Remember what I said yesterday, without teaching it, I'll be in the weeks to come, is that when I wanted to write, for example, the the electron mass, I had nu EL and ER. There was no way I could write a mass term out of a doublet and a singlet. So I said I can do the following. I can write something I call a Yukawa coupling, then write nu E bar L. Then we decided, someone helped me, that we needed a scalar doublet here, ER. This is called the Yukawa interaction. When I say scalar, I mean under Lorentz. When I say doublet, I mean under SU2, of course. And then I said, if it will happen, we call it like this, a vacuum expectation value, that this is non-zero. I wrote it like this in the vacuum. If that was to happen, it would break SU2 symmetry, obviously. Because even when there is no energy, there can be no SU2y. From here, we will get Yukawa E, EL, ER, plus Hermitian conjugate. But no nu L. There is nothing here to be here. No nu L bar and whatever is there. There is no right-handed neutrino. This is called spontaneous symmetry breaking. We have to learn how to break symmetry, and that we will start very soon, not today. Before we go on, I've just summarized the picture that we derived once again. I like to start by reminding you where we stand. First things first, let's see what we really mean by massive gauge boson. After all, this is the mediator of the weak interaction, and you should have a good understanding what it means and how it connects with the Fermi theory. So before I go in all of this, which is the subject of the standard model, this will be the subject of what we are after. Okay, this is our task, okay, to be studied. Let's speak about massive gauge fields. What do I mean by massive W? The theory of massless gauge bosons is called the Maxwell theory. This is called the Proca theory, studied by Proca. And let's just do U1. He studied U1. You and I will always start with U1, whatever we do, whether it's symmetry breaking, whether it's the symmetry principle, because there where the essence lies, the rest is group theory. And Proca writes the Lagrangian the same way the Maxwell would. You have the kinetic energy, which has the good Lorentz behavior, but apparently you are told that the gauge boson has a mass. So you write the mass term. I can rewrite this slightly. This is minus a half. Because of the anti-symmetry, I can write like this. Instead of the quarter, I just write the half, because the second piece, because the anti-symmetry will just repeat it. And of course, with the same mass term. I integrate the first by part. And I get 1/2, the sign changes. I drop the total derivative. I will have, obviously, look, the first piece is going to give me the box. And the second piece is going to give me a mu. I wrote it there. D nu, d mu, A nu, plus the mass term, which is written there. I can write this in maybe slightly more elegant manner. A mu box plus m square g mu nu minus d mu d nu a nu. I didn't have to do that. I could have written the equations of motion. It's just sort of, I don't know why I did it even. You and I know how to write the Euler-Lagrange equations of motion. But from here, you see, I have a quadratic form, so I can also look for the propagator. I can do two things: find the equation of motion for my field, and then find the propagator. Okay, so the first step is the equation of motion. Let's see what we get. Obviously, we'll get this. You are going to reproduce it. You'll have a homework. Oh, you got it? Sorry, I've sent it to you. Some of the steps that I skip, you will make sure that you go through. There is nothing like doing the homework. I must tell you, the grade depends heavily on the homework. So of course you should do the homework. It's not just the exam. It's about half of the grade comes from the homework. Well, maybe this year a little less, we'll see, because this course is accelerated. Unfortunately, there won't be so many homeworks, but still. I can take a derivative of this d nu acting on this. Notice what I get if I take the derivative. I get the box plus m squared. This will give me d mu a mu minus. This will become, again, no, I have something wrong with the indices, right?
Yes, the a nu should be a mu in the first.
Maybe you are saying this is the a mu?
Yes.
I think it's better. Thank you. And we will get here, obviously, again, d mu of box a mu. The order, of course, they commute the derivative. So notice that the first term cancels with this term, and you get m squared d mu a mu. Remember, in the massless case, of course, you would never get this equation. It had to be imposed as a gauge condition. But I'm deriving the equation of motion. There is a mass term. There is no gauge redundancy. There is some redundancy because from here you get the central equation of the Proca field, which used to be a possible gauge condition. It was one of the possibilities. Now it's simply a must. It kind of eliminates this longitudinal and extra degrees of freedom, not the time-like, sorry. Why? Because this is a massive spin one field, which means 3 degrees of freedom. It's a massive particle, so I can stop it. Unlike the photon, I can never stop the photon. So in the case of photon, I talk of helicity. I have 2 degrees of freedom. Massless particles have 2 degrees of freedom. We'll be talking about helicity very soon, maybe today, if not tomorrow. Well, now we have a well-defined massive field that you and I can stop. It has 3 degrees of freedom. So degrees of freedom, I will often write like this, degrees of freedom. But a mu has 4 components. So obviously, in order to have 3 degrees of freedom, this eliminates the unphysical degree of freedom. This is not surprising that something like this would emerge. Very good. That's T mu A mu. What do we want to say? So let's look at it a little bit. let's imagine it at rest. So let's take the Proca at rest. By the way, when I say at rest, I should have gone to momentum space. Actually, I can write A mu as a Fourier transform, or let me just have a fixed momentum, epsilon mu of P. Just think of integrate over all the ones. The thing is that when you write this, the P component, you have P mu, epsilon mu of P equals 0. This is the Proca condition in the momentum space. Epsilon mu is called polarization tensor, right? Now, what happens when I go at rest? When I go at rest, I have only rotations to worry about. There is only rotations of the spin 1. And I hope that you remember, if not, you should rederive it, that the form of this is called an adjoint representation, adjoint to the generators. It has this form. This matrices satisfy the commutation relation of the rotation. That means SO3, but SO3 is the same algebra as SU2. Sometimes I will use the name group. I will be very careless. I won't be mathematically rigorous. Because for you and me that are looking at small transformations, for us, the only thing that matters is algebra. I only worried really about the commutation relation. The same as the Pauli matrix is satisfied. This is the same algebra. Of course, SU2 is a covering group of SO3 because you can have spinors, but this is the dividing representation. If you wish, SO3, after all, is an orthogonal matrix that you can write as E to the theta I Ti. Just write like this, O transpose is 1. SO3 determinant O is 1. Since this is real, Ti must be imaginary. And from O transpose, you get immediately the Ti is minus Ti transpose. There are 3 such matrices. Here they are, precise. Normalization factor comes from the need to satisfy commutation relations. This you should remember. But if not, here it goes. Please ask me if there is anything not clear. I won't check the commutation relations. I know they are true. If you have any doubt, please check them. But in a sense, it's obvious because really what I'm saying, I'm just saying that they have to be, of course, traceless. Determinant is 1. Also, the trace of Ti is 0. Determinant of O is 1. So T3, for example, let's give just an example of, this is what I mean. Because of the property of orthogonality, they are anti-symmetric and imaginary. You can see that this is a unique form and it's traceless. This element must be 0 due to tracelessness. And the form above is the dictated by orthogonality. T3 must be minus T3 transpose. I know how to diagonalize this. I know how to solve the eigenvalue problem. This is very easy. look, if T3, you can check immediately, acting on this state is 0. It's trivial. This is a state of the eigenvalue 0. T3 acting on this is I to the minus, so it gives me 1. I times 1 gives me I, 0. I got a state, so this is eigenvalue 0. This is 1 eigenvalue. Eigenvalue 1, I could have changed another order. Of course, you should know that. And T3, if I act on minus I0, becomes, what does it become? Becomes minus 1 I0. This is, sorry. This is minus 1 I0. This is eigenvalue minus 1. Well, that's what you know. You know that spin 1, of course, you know that spin 1 has eigenvalues. Spin 1, of course, is equivalent with eigenvalue 0, plus 1, minus 1. But you know from quantum mechanics. I'm just reminding you here. In other words, my polarization tensors are, remember that epsilon mu, p mu is 0, and we are at rest. So that means that p0, sorry, is m. Plus being at rest implies epsilon 0 is 0. So I know my polarization tensors. I have epsilon plus and minus equal 0. I'm going to write it horizontally, not vertically as it. Then what did I have? I had 1 plus or minus I0. I will normalize it like this. And then there is with the eigenvalue 0. This is 0, 0, 0, 1. They are normalized the same way. Let me write epsilon mu. This is now a 4 component. This is your polarization tensor for the Proca field. We can do everything when we have a polarization tensor. Well, let's, you're saying that's at rest, but I want to know what happens when it moves. So let's make it move. Let's boost it in the z direction, say. I can always choose this to be the z-axis. So now boost in z direction. And what I get is that epsilon mu, and now I call it transfers because this is now orthogonal. They, of course, are unchanged, are 0, 1, plus or minus I. There are 2 transverse components. I normalize them. and since epsilon 0 prime is epsilon 0 plus v epsilon 3, and epsilon 3 prime is epsilon 3 plus v epsilon 0, I get that epsilon mu, I call it longitudinal. It's in the direction of motion. So there are two of them. I could call them plus minus, and the third is one longitudinal. It won't be zero anymore. It's easy to see that this is P over M, where P is the momentum. In other words, P is 0, 0 in the Z direction. P over M velocity. Then I have 0, 0 E over M. This is your polarization tensor. Notice the way they are canonically normalized. Epsilon mu is -1, the way we normalized. Okay. From the form of these guys, you can immediately derive. You can do it at rest or you can do it in motion. You get another important thing, very important, that the sum of epsilon mu I, there are three of them. I is 1, 2, 3. What I mean that I goes through plus, minus, and 0. These are the three polarization tensor I star. Someone knows what this is? You ever derived it? It turns out to be equal to minus G mu nu minus P mu over MA squared. It's trivial to check it. Check, please. Let me put an asterisk. Maybe it's in the homework. I don't even remember whether I included it. I forget now. This is a very important relation. Well, it's not so surprising. It satisfies what it does here. There is, at the end, you can say, well, it's obvious because you can tell me, well, this sum of epsilon mu star must be some. I mean, after all, what tensors do I have? I have G mu nu plus B combination P nu over MA squared to have proper dimensions. And then I know also that P mu, however, epsilon mu is 0, for example, or P nu epsilon nu. And then that fixes B equal minus A. And it turns out the normalization is such that you get a minus sign. So that you immediately get that sum epsilon mu star is proportional to G mu nu minus P nu without computing. All you have to do, take one element. So I take 0, 0 element and I find out the coefficient is -1 without even computing. Okay. This is it's clear sort of what the Proca field is. It's just a spin one state with a well-defined mass. You see what I've done? I've just diagonalized this operator, this generator, if you wish, T3, which you knew would have the famous 4, 1, 0, -1. Okay, I wrote it explicitly so that you have this polarization tensor and so that we can comment on something very important. See, the name here of this guy is longitudinal, is justified. This guy is in the direction of motion, so I call it longitudinal. And they are all commit, so obviously I will call them transfers. If you move in the direction 3, you are in the direction 1 and 2. Okay. Is it clear? I think this is what I want to say about the field. The next step that I do, what you do whenever you study the whether it's a scalar field, Clyde-Gordon, or you're studying the Spinoria field, you compute the propagator. You have to find the propagator, and this is the quadratic form. What is the propagator? Is the inverse of the quadratic form. So let's now move to the propagator. This is 0.2 propagator. I wrote the Proca Lagrangian as 1/2 a mu box plus m square g mu nu minus d mu d nu a nu. This becomes 1/2 epsilon mu minus p square plus m square g mu nu plus p mu p nu epsilon nu in momentum space. And this is your homework. The propagator of the Proca field, the Proca propagator, let's write it, is with usual conventions as in the photon case, is what you would guess, just like the Klein-Gordon. It's going to be p square minus ma square. And you have two tensors at your disposal. One is g mu nu, and the other is p mu. And it comes out. Notice a few things. Let's see a few things which are worth commenting here. You will derive it. You will feel more confident when you derive it, of course. And maybe you could have said, I don't even have to derive it. I'm a physicist, so I can think a little bit. Notice that from here, that delta mu nu Proca is actually I over p square minus ma square. Then I go back and I see that this tensor, g mu nu minus p mu nu, is actually the sum of the polarizations. It's actually this. Over these three polarization, a very interesting result. But I could have guessed that. The same thing happens from spinor. After all, I'm propagating 3 scalar degrees of freedom. What is this here? This is the propagator of a scalar field. Right? This you know. And you have 3 such scalar fields whose sum of the polarization tensor is precisely this g mu nu, p mu nu combination. So it's not surprising that what you are doing is simply propagating those fields. Okay, this is the physical interpretation. This is sum of polarizations. So it's kind of nice that the physical intuitive picture works. Now, one important thing. You know that if you have a Clyde-Gordon field, the scalar field, the propagator is I over P squared minus M squared. If you have a spinner, you have the propagator, which is IP slash minus M. If you have a photon, you have a propagator that actually you can write as 1 over P squared. That is G mu nu in the gauge that Feynman like. For example, I can choose this one, call it Feynman. Notice the joint characteristics of the propagators up to now. All these propagators, they have one thing in common. All propagators are proportional as 1 over momentum when P goes to infinity. They vanish. And you can say, thank God that they vanish. Because you see, you are saying to yourself, when I do my scattering amplitude, for example, electron on electron, and I exchange at 3 level 1 photon at the loop level, you're saying, I'm going to have to do this thing at the loop level. I have to do the loop. And how do you do the loop? You integrate over the internal momentum K. And then you plug in the propagators. And then you're saying, oh, it's nice. At large K, I have 1 over K squared from the photon. I have 1 over the K squared from the photon. I'm writing just symbolically. I have 1 over K from the spinner. I have 1 over the K from the spinner for large K. I'm just interested in what happens from large K inside the air. And you are saying this is great because this is D4K, roughly 1 over K to the 6. This is finite. There is no ultraviolet divergence. You have a lot of Ks in the denominator. This is what you like to achieve. This leads to renormalizability. This is the reason why the theories of nature that we like UD, are renormalizable. Or even a scalar theory would be renormalizable. And the reason is that the propagators have nice behavior. They vanish when momentum goes to infinity. Otherwise, I mean, just to understand, so this is with a photon. This is obvious. Look at the case of Proca. Let's do the same thing for Proca. After all, this could be 2 Ws. By Proca, really, or 2 Z bosons. I mean, Z boson is really a Proca field. So I have these two, a Proca, let's say, a Proca. In this case, this loop would give me D4K. Now look at the behavior. Oh, before I do that, I'm very sorry. I'm interested at the large K behavior. I forgot. Let me go back. I should have said immediately. Look at our propagator. So I have to go back. Let me pause. I need for this delta mu nu Proca is it behaves as 1 over K squared minus MA squared. But if K is very large, so I'm going with K to infinity, I can drop this. I have G mu nu piece that's well behaved. Then I have another piece, which is P mu nu. But P mu nu in the symmetric integration, or K mu nu, sorry, this is K now, behaves as K squared, again, G mu nu over MA squared in the symmetric integration. This is the behavior. So notice the first piece is okay. The first piece, number 1, erases so easily. Number 1 goes to 0. But look at the piece number 2. Goes into 1 over MA squared. It does not vanish at infinity. And you can see this is going to create a disaster, and you can see immediately. So the Proca loop, immediately you get. We don't have to do any fancy. There's going to be an integral over d for k. There'll be two propagator square and two fermions, each of them going as 1 over k. This is a disaster. This is proportional to 1 over ma to the fourth. D for k in the symmetric integration is like k squared dk squared over k squared. And you integrate. Okay, I'm looking just at some large behavior. Don't worry what happens for small k. This is not correct for small k. You can do this calculation if you want very rigorously. I'm just interested in the behavior in the ultraviolet region, as we say. This becomes proportional to lambda squared over ma to the fourth. And lambda is supposed to go to infinity. This crazy thing diverges. You could see that there is going to be a problem. This is the famous problem of the massive gauge field that led to one of the greatest revolutions in modern physics, which is the Goldstone and especially the Higgs mechanism. Glesher knew that in 1961. Glesher knew that there was a problem. It was pointed out. This problem was pointed out in 1960 by Weltman, who was an advisor to 't Hooft, who completed the standard model, and Van Dam, I think. I don't remember. I'm not sure. Weltman and Van Dam, the two of them in 1960, just 1 year before Glesher. So Glesher said, I'm aware that there could be a problem. We'll have to come back to that. I mean, today we are not going to worry, you and I, about the large momenta. We are going to think of weak interactions, but I want you to be ready to know that there is something strange about the Proca propagator. This piece is worrisome. We'll really have to struggle to understand what to do with it. And I want you to understand it in simple terms, not in some formal, field theoretic language, okay, that comes much later. You see it here. You and I want to get rid of this piece. You just don't want it there somehow. I don't know how we'll do it, but we have to get rid of it. Otherwise, we won't be able to compute. Good. We'll come back to it. This was a digression, just to give you a flavor. Don't worry if it's not completely understood, please. Ask me a question if you want to know more, but don't worry. You'll be hearing a lot about this. And you'll compute certain things. I will now not worry about the large momenta. I will now summarize it. So I have my delta mu nu Proca. I will write it once again, minus I, in order not to copy it. And I will look at it. P nu over ma squared. And I will imagine that my Z boson, let's say a Z boson or W. Let's take W. W, after all, is a Proca field. It's charged, but there's just a personal internal characteristic. It's massive, so it will. After all, W is made out of two. Remember, W is made out of these two A1 and A2. It's just a complex version of the Proca. Each of them has the same propagator. So that's W. So that means that when I have my weak interaction, and what is the weak interaction? I used to say that neutron becomes proton. Well, as you know, it's down quark that becomes an up quark. We should stop talking about the proton, and we are at the quark level. Down quark emits a W, and it's W minus going in this direction, so that the charge is conserved at this vertex. So this is an electron, this is neutrino entering. And that means At each vertex, I have G over square root of 2. So this gives me G over square root of 2 squared, UL bar, gamma mu DL. Then I have a propagator. Let's not worry, please, about the factors of I and so on, which I'm not interested in the sign of this, just in the form. So what do I have? Help me here. I have G mu nu minus, let's call this momentum exchange Q, typical name for exchange momentum, Q mu, Q nu over MA square, over MW square, sorry. For physical W and Z, we tend to use the capital letters. So let's stick to that. Most of the people, MW square divided by Q square minus MW square. And then what do I have here? I will have EL bar, gamma nu, nu L. EL is going out, nu L is entering. This is my amplitude for beta decay. And you know, how did we get weak interactions? By saying that Q is much smaller than MW. We go back to the old days. They were even at MEV, but you can go to GV, you can go to few GV. As long as Q is much smaller than W, this becomes G square over 2. I can neglect Q square. In this case, I can neglect this. See, unfortunately, this troublesome piece is opposite from being troublesome, simply does not contribute. Compared to G mu nu, which is 1, this is 0. This is the beauty of the low energy aspect of the standard model, immediately reproduces Fermi theory. And I get, what do I get? I just get MW square up to a sign. This is proportional. No, proportional, it's just up to a sign. So let's not worry about the sign. G square MW square UL bar gamma mu DL EL bar gamma mu nu L. This is, in other words, from here immediately you get the G Fermi over square root of 2. Fermi wrote this interaction. Of course, he called them proton and neutron. Is equal to, sorry, there is a factor of 4 in the definition. When you use the chirality, you get the connection between the Fermi theory and the propagation of the W boson. You see, Fermi knew that there could be a W boson, and he didn't use this language because he says, what am I going to do that? I don't know G, I don't know MW, what can I do with this? It's just a way of rewriting in a more complicated manner. It doesn't really help me. You don't understand Newtonian physics by writing that G Newton is 1 over M Planck squared. That's just a way of writing. Unless you have a more fundamental theory, for example, like Einstein theory. But you see here, there is a difference in the standard model. Remember, G is E sine theta W. So I can write that G Fermi over square root of 2, the famous weak interaction, is equal to E square over 8 MW sine theta W square. Now, if I write this, unless I know theta W, okay, again, this would be relevant formula. I could have pretended that this is true. It will not help me unless I know what theta W is. You need for this the weak mixing angle. This is very important. And this is where the full, if you wish, strength of the standard model comes in. Because what Gleschov can do that you couldn't do before you had an SU2 cross U1 gauge series. Remember, Gleschov proved that there is a Z boson whose current is given precisely, it's proportional. Let me just write without the fields, minus Q sine squared theta W. So now it's all done. You measure it here. This measures theta W. We measure theta W in weak interaction processes because sometimes you scatter an electron, sometimes you scatter a neutrino, sometimes you scatter an up quark, and so on. Every time you have a universal form with a different coefficient, and you determine theta W. And this is the famous thing. Remember, we said theta W is roughly 30 degrees for me. It's roughly a quarter. Sine squared theta W, well, more precisely, sine squared theta W is 0.23. This is what Lep taught us. The high precision experiments. And therefore, I can tell you what the mass is. I know everything here. I know E squared. This is 4 pi alpha. And you measure alpha, you measure theta W, and you get the prediction that MW is 80 GeV. Checked already roughly at the discovery time, but left confirmed this spectacularly to a great precision. You can now do loop corrections to this. Standard model is a high precision theory, and the agreement between experiment and theory is fantastic. What Glashow couldn't, he couldn't predict the Z boson mass, but he could do a similar thing. He said, look at the neutral currents. So instead of looking at the beta decay, he said, look at the processes in which one fermion is scattered on another fermion in a neutral manner. For example, F1 comes in, F2 comes out. You could exchange a photon, but you can also exchange the Z boson and put here F2. Look, do the following. Take this to be neutrino. Then this is not a photon, this is a Z boson. And of course, you can measure the strengths. You do the same thing. I'm not going to write it because the formulas are complicated. But from here, you can measure MZ. That's what people did in the experiment. And the number was 90 degrees, 90 GeV. It's almost the same. This is experiment. Glashow theory. SU21 cross U1 does not predict. You can never predict a single mass. Remember that in the standard model, there is no way predicted MW. We don't predict the masses. A fundamental mass is an input. We correlate it in a good theory, and we'll talk a lot about that. But I can't predict MW because I need to measure theta W. It's correlated. I'm correlating the W mass to the strengths of the weak interactions, G Fermi of the beta decay, and the value of theta W. Does not predict the ratio, say, of MW over MZ. That has to be measured, okay? This will be determined later. This will be determined later through the Higgs version of the theory, Weinberg-Salam work, to be taught. But at this point, please remember that I cannot predict it. Okay, this will come later. And this is as good moment as any other, I believe. Let me see if I want to say something else here that I forgot. I think I'm okay. I think I'm okay. You have a question here? An urgent question, please. Some of you told me that you didn't know much particle physics. And if you didn't know much particle physics, you ought to have a question on what I'm doing here. I don't mind answering any basic question. Please. The only way to learn is not so much by reading, by it's much more by asking, doing homework and stuff like that. Okay. What do I want? What else do I want to say? Nothing. I probably let me still pause. I want to pause on purpose just to see if you guys think that there is something. Remember what we did? We derived the propagator, we exchanged the propagator. We argued that at small energy, this piece K nu is irrelevant. This helped us a lot. K square is small. And we could find this correlation. Okay, so once again, I finish on this note. The G Fermi, when I write G Fermi over square root of 2, I could have written 4 pi alpha to have a more complete. Call this alpha electromagnetic to be clear what I'm talking about. And then there was 8 MW sine theta W square. Okay, so in other words, this measures weak interaction. This measures electromagnetic interaction. You see how it is nice? We are correlating the strengths of the weak and electromagnetic interaction, and this is coming from neutral current. There is a profound correlation in the standard model, in other words, the Z physics, Z mediated. And although it was not prediction of numbers, you should appreciate the beauty. The physics is about correlation of otherwise seemingly different physical properties. Okay, this is what the standard model does. Okay, very good. I can stop here. Let's meet back, please. In a nice number would be 1210. Give you a chance to please think about what could not, maybe was not clear and you was not aware. We are back in 6 minutes. Okay, we are back. Any questions, please?
I have a question.
Yes, please.
We used G prime and G, the coupling,
Right.
yesterday, but today we are using G, but
G prime, you said, right?
yes.
There are no two couplings if I introduce tan theta W. I have traded. So what I've done, I have introduced tangent theta W. So from here, what I've did, I have traded G and G prime for G and theta W. I can also trade them as I did. I have a choice of what to use. It's always up to you. I also chose to use E and theta W. If you don't go back, not even G. Why? Because E is G sine theta W. So it's up to me which of the two. The trouble is that there are two of them, not one. It's not a fully unified theory. I'm glad you asked this. So, okay, we have a little digression. Okay, let's forget this. We'll come back to it. I don't have to erase it. So this is very important. The standard model is not a fully unified theory, okay? Not fully unified. Not fully unified. What I mean is it needs two parameters, two couplings. Need two couplings. You choose which one you want. It's up to you. You can work with D and G, you can work with D and theta W, you can completely free. But since the world chose theta W and everything is said in the form of theta W, nobody's going to tell you what G prime is. Let's stick you and I to using theta W. It's somehow universal, universally chosen. It won over the others. And then whether you use G or E depends how you like, okay? It's, I hear something. There is someone is not muted, please. If you are, unless you're asking a question, you should be muted. Is this clear? Did I help?
Yes, thank you.
Sure. Any other question? I want to move along. And just I wanted you to remember roughly that E is 1/3 and G is roughly a half. Roughly, this is very rough. And theta W is roughly 30 degrees. I'm happy if you just roughly have an idea of these numbers. We are really lucky. Although E and G are not small, we find out because of this value that alpha electromagnetic, which is E squared over 4 pi, is roughly 1/100. And alpha weak, which is G squared over 4 pi, it's roughly 1/30 or something. Okay, you can put the numbers. Okay, it's 25, 1/30. So we are lucky that these are small numbers. And that means that implies good perturbation expansions. This is the great thing. And this is very important for you and I. Really, the only thing you and I know is how to do is perturbation theory. When I talk about QCD, I'll have to remind you that we have no way of analytically computing anything, basically, when the QCD coupling gets large. We use these computer simulations, Monte Carlo, whatever lattice it's called, etc. But it's not an analytic expression, okay? So let me write this later, and let me count. Okay? Let's talk about how to discover W. And the properties. I don't want to just talk how to discover it. I wanna do something else. Really, what I want to talk about here, which is very important, is the parity violation. Because in beta decay, it's a three-body decay. It's terribly hard to compute anything, and it's murky because of nuclear physics. You and I are going to do something beautiful by producing W at lab and studying its property. You will finally see the maximality of parity violation by doing a homework. It's nice that the homework that will come, where yesterday research, we are now, you are now at this stage of it, going through a phase transition of becoming researchers. And the standard model should be the ideal place to do it, where you learn both the rigor and the fun with field theory, and also learn and also appreciate the boring detail of getting the signs and the factors of two together. Doing research is always oscillating from fun to boredom, to fun to boredom. Yeah. Find the right amount. If you just compute, it's boring. If you just think, it's incomplete. Okay, parity violation. So how do I produce the W? Well, I take a machine. I take P plus P bar. And I take, say, I don't know, down quark here. I can choose up quark here. So I have my down quark coming in, anti-up quark coming here. And that will produce the W boson. Right? W minus will be produced. The sum of the charges is -1. And it will decay, W will decay into whatever we want to study. We can study decay into electron neutrino or into quarks again. But the crucial thing is the following to understand. I have talked about the chirality. Remember, this guy is left-handed. What about U bar? Who can tell me, is it left-handed or right-handed?
Right-handed antiparticle.
Thank you. Precisely. Actually, I'm very cavalier. When I write U bar, I really mean UC. Remember, the field that has proper Lorentz transformation is UC, but it's basically U bar. And remember, when U is left-handed, UC becomes right-handed. This is what I mean here. This will be very important in a second. Now, chirality was sort of, what was chirality? You have this sort of thing that psi LR was a projector on psi, and LR was this funny combination of 1 plus minus gamma 5/2. It has absolutely no physical meaning, chirality. Why it doesn't have a physical meaning? Because when you have a mass term, you go from psi L to psi R. So you can't tell someone that the particle is left-handed or right-handed. Of course, you can tell them, look, I don't know what the particle is, but when they see the W, in order to see the W, you have to be left-handed. But the particle itself, I can stop the guy, and the guy doesn't know whether it's left or right, okay? So the thing to understand chirality, so it mixes left and right. Of course, then you say, but then let me go to the m equals 0 limit. That's what I need to do. And everything is clear. Now left cannot become right. Now psi L is Lorentz invariant statement. I can't make it become right-handed. For this, I need a mass term. And, you know, I can do that by looking at the Dirac equation. Let me just remind you, I hope that you know that. Dirac equation says that P slash psi is M psi, but this is 0. So I have P slash, and remember in my notation, how does P slash look like? This is 0. This is E plus P times sigma. Remember what my off-diagonal matrices were? E minus P dot sigma 0 UL UR. When I break into two components, now it's very easy because they are separated. Plus sign because it's a four product, right? I mean, P mu gamma mu is P0 gamma 0 plus Pi gamma I, which is P0 gamma 0 minus Pi gamma I. There's a minus sign with those gamma matrices becomes of this form. Okay, so what I get immediately, oh, I made a mistake. Sorry, this is the minus sign. Why I just said it. This is a minus sign. Why did I change the sign? So I get that E acting on UL or R is plus, no, minus, sorry, minus plus U, so, sigma dot P UL, right? This is the equation I get. And then I just remember that P is P times the direction of motion, but this is a massless particle, so this is energy times direction of motion. And then I remember that the spin is sigma over 2. So I get energy will cancel, notice that U left right is 1/2, I can write, is S times P. And what are the signs? U left right, there is a minus or plus sign. I introduce a famous helicity, a projection of the spin on the direction of motion, a characteristic of massless particles. Photon has two helicities, plus or minus 1. And obviously spinors have massless spinors helicity. So I get that H acting on ULR is minus plus 1/2 U left right, please. Let me write it in the boring manner, something that we will never forget. HUL is minus 1/2 UL. HUR is plus 1/2. Plus 1/2. You're right. This is very important. We made a decision. This is what I mean by left. Just like for us, left is where the heart is. We have a definition of left with a negative helicity. With the convention. Well, here there is a symmetry, so I've chosen randomly. Okay, no, I shouldn't do it. Okay. And we have to stick to this, by the way. This is now, it doesn't matter whether L is 1 plus minus gamma 5. Gamma 5 is defined up to a sign. But once you made your convention, it has to agree with this. This is what everybody is using, okay? This from now on, your left-handed spinner must have helicity minus a half. That you cannot change anymore. You have the right to change your conventions for gamma matrices and so on. Gamma 5, but you cannot change this. You have to be consistent with yourself. So in other words, when M is 0, the bottom line, in the nutshell, summary. When M is 0, I get that helicity is chirality. They agree with each other. So the mass term, I'm allowed to change the chirality, of course, the helicity and chirality by that notion. Therefore, when I'm at very low energies, when the particle is massive, this notion makes no sense. But remember now, imagine that you want to produce, you go back to this picture. Look at what happened here. Let's go back to this picture here. You see, let's draw it again because sort of going back, this is, you know, on the blackboard, I would just keep it on the blackboard, but I don't want you to go back. So once again, I had my down left-handed core, which is hitting on the UC, strictly speaking, I should have written, by the way, which is right-handed. It changed the chirality. This is very important. So let me ask you, what is the helicity here? Who's going to help me?
It's
minus a half, right? And what about helicity here? What is it?
-1/2.
Sorry?
-1/2.
No,
Minus a half.
no. This is a right-handed spinner. This is what I keep saying. It's made out of the up quark, but now we changed it. We went into the anti-state. I have a left-handed fermion. I can work with the charge conjugate. Look, you have to put a bracket to see what you mean. But this is the right-handed fermion. We found explicitly the lower component then became a upper component and vice versa. This is plus a half. This is very important to remember. This is crucial. That you cannot doubt. You just look at you are saying to yourself, if the left-handed fermion couples to W, that means it's the right-handed anti-fermion that couples to W. Particle no antiparticle is a mirror transformation. It's a left-right symmetry. Charge conjugation is a left-right symmetry, left-right operation. And remember why it happened. Let me just remind you again. CFL bar transpose, let's write, is I gamma 2 gamma 0. Then from there is another gamma 0 from F bar, and then I get FL star. I'm simply saying that F bar in general is F dagger gamma 0. So now I take a transpose, I obviously get what I get here. and this is I gamma 2 FL star. And this, remember, was off diagonal. I sigma 2 minus I sigma 2, 0. UL star 0. This is 0 minus I sigma 2 UL star. This is a right-handed spinner. Remember what, I mean, it's funny, this for left and right should be up and down, but it's the way it is. An upper component is left-handed with our conventions, and the lower component is right-handed. So this is a right-handed. And therefore right-handed, you don't have to think anything of how you built it or whatever. In the weak interactions, the antiparticle will always be right-handed. The particle will be left-handed. What does it mean? Where is the spin of DL pointing? Who can tell me in which direction is the spin of the DL pointing?
It's opposite to the direction of momentum.
Right. This is the spin here. What about this guy? You see, where is the spin pointing now?
In
For
the
this
same
guy?
direction.
Yes. Notice what we achieved, an incredible thing. It seems impossible. Actually, you were saying, how in the world I'm going to polarize a W boson? But we actually polarized it. Call this a Z direction. I don't know, call it whatever, but let me call it Z. I have just polarized S, Z of W is +1 or -1, whatever, I'm sorry. Depends which direction. Okay, my Z is going to the left. It doesn't matter. It's a convention. At the first even machine, whenever you produce W, doesn't matter. Why? Why am I saying this? Because the quarks are massless. Oh, I forgot to say. Oh, I'm sorry, very, very much. This is what you have to believe. M up is of order or M down. I'm very sorry. It's of order of few MeV. I'll come back to this. Just take my word for this. We'll talk about it, I promise. Therefore, since the energy of the process is of order of MW at least, you cannot be less than MW because you want to produce MW. Therefore, the energy of the down and the U bar is bigger than or equal to MW over 2, which is 40 GeV. Just we are now in the center of mass. That's how we are producing the W, which means then M up, M down over energy is basically 0. We can ignore it. It's a terribly small effect of order 1 in 1,000. Well, if you want to do 2 loop calculations and so on, you'll take into account, but we are going to do 3 level. At the 3 level, this is completely negligible. In the limit of very high energies, this is why chirality becomes a very useful and helicity concept in particle physics, because we do high energy experiments. What do I mean by high energy? I mean energy much bigger than the masses of the particles involved. At TV now at the LHC, which is 14 TeV, we are far above any of the standard model particle masses. We are in the high energy regime. This is what we mean by high energy. It has to be relative to something. We have truly become high energy physicists. Now for sure. Previously, we had to say compared to some mass. For example, W itself, we were always below W mass. Now we are far above W mass. So when I produce the W already at that stage, I produced, in other words, what it means, the W is produced and it's polarized What does it mean that it's polarized? Well, I can study parity violation because I have a direction. Because you could tell me, how can you talk to me about parity violation? W is at rest. I'm going to produce W at rest. So no direction of motion. To simplify your life, we'll take W at rest when we look at the decays. We can always boost it to understand, but calculation in a boosted frame, it's hard. So we'll do W at rest. And the direction is provided. This is the W Z component, the spin. And it gets produced with a well-defined polarization. This will enable us to do to check the manifestly whether parity is violated or not. Any question here? This is very important, this part, physically. Sheer luck. In other words, when I have my W boson, I can say I start with, say, SWZ equal +1, I can say. I can call it -1, but that's just a convention. Of course, the result will be the same whether I take plus or -1, and you will check that in the decay amplitude. That's just convention of the direction. Okay, so if you wanted to compute, you and I would want to. So the next step to do is to compute W decay. Now, the next step, it decays, say, into, just to appreciate that, into left-handed electron, plus, sometimes you write nu C. I will often write nu bar, just to, what I mean by either I write nu C or nu bar, it's just a way of simplifying my writing. In the books, people often write nu bar. This is how W minus corrects. Now, what about nu bar? Is it left or right-handed?
Right-handed.
Very good, right-handed. It can also decay into the down quark again, plus U bar, which we learned is right-handed. These are the principal decays. Of course, remember, there are more generations. I'm pretending there is one, but I will remember that there are more, and you will remember that there are more. We'll include them when it's necessary. And here, the only thing to say is there are no free quarks. When you look at the experiment, they hadronize. You produce the, what we call the jets. In other words, when W minus decays, it was at rest. So you get, say, down quark going this way and up quark, anti-up quark going this way. What happens here, these things become actually, and they pick up a lot of velocity. They are massless particles basically, so they move with a huge energy of 40 GeV. But as they are going away from each other, they hadronize. This is called quark confinement. Just to tell you, what happens is that you produce a jet, really, of particles like pions and such. This has been observed. I'll come back to this, okay? And here you get a jet. It doesn't matter. We can talk about it later. This is a mess. I don't want to talk about it. I want to focus on the simple fermionic decay, not worrying about how we see them, okay? So we are going to just pretend that these are like leptons, okay? The next thing for you and I to do is to compute W decay, partial decay amplitude. into light, and by light I mean mass zero. I will ask you to simplify your life by looking at the mass zero limit fermions. That's what we have to do next. We know the interaction. The interaction is g over square root of 2. It all starts from L dl w mu minus w mu plus, which gives me the amplitude g over square root of 2. Let's say I'm now let's take neutrino and electron for simplicity. So instead I'm gonna write nu L bar gamma mu EL epsilon mu of W in the momentum space. So the amplitude will have the form. I don't know whether I should start it now. It would be better if there were questions. No, I shouldn't start. Not at this time, not even start. It's time to wrap it up. You know, the thing that I mentioned en passant, when sometimes I want to bet your imagination, okay, please don't feel bad if they're not clear, the things when I mentioned hadronizing and so on. Is it just kind of to not to be just boring going through the algebra? I'm not pretending that I'm explaining anything. I'm just bringing something to your attention that you can ask or we can come back to. Next, to tune on tomorrow, partial decay rate. I'll try to skip a number of steps so that I'll try to skip certain things that you will give you understanding only if you perform them. Any questions? I'll give you another. Okay, remember that today at 4 we have office hours for those of you that do have questions and want to ask them, you know, in a more concentrated manner. Okay, that's it then for today. I may see someone at 4 o'clock.
Thank you very much.
Thank you.
No.